So if there are questions that come up, please ask as we are I'm reviewing. So today we're going to continue our discussion of renormalization group by talking about Kalin-Simanzik equation. So as usual, we start with a review of what we discussed last time, renormalization group. In simple terms, the idea of renormalization group is something along the lines of the principle of separation of scales. There is long distance physics, low energy modes, short wavelength, long wavelength modes, and then there's short distance physics or high energy modes. And these two are quote unquote kind of decoupled. The low energy physics does not rely on the details of the high energy physics. Now, there is a little bit of a lie in that it does so no, it's not a lie. What I have to clarify is that what I mean by details. The idea of renormalization is the following idea, that everything, all the details of the UV physics, all it can do is just change a bunch of, really a handful of coupling constants and wave function normalization. That's the effect of all of that could be absorbed this way, right? This is the idea principle of separation of scales. So when you look at the correlation functions of low energy degrees of freedom, they're independent of the cutoff of the theory, right? Now, one thing that I have to say, because we've discussed this, if you have think about the spin system. Think about the spin system. I'm just going to make an analogy with classical physics. Well, I'm going to give an example of classical physics, right? So if you're looking at long distance physics, the excitations that are long distance are, let's say these are rotors, right? So they can rotate. Long distance excitations are things like this, right? This is a long wavelength excitation. Now, do you see this? This is a long distance excitation. Now, what does it mean to say that it's insensitive to UV details? It means that if you take one of these guys, and this covers an Avogadro number, like an absurd number of sites, right? If you take a bunch of these guys at different points and flip them, rotate them, the structure of the wave, even with your eyes, the idea that your brain can actually see that, oh, you might not even see it, right? So that is a little bit like renormalization. As you average out, that's what renormalization does, right? You integrate over all these modes. As you average them out, that is washed out, right? That is basically the idea of it. There is an error correction code actually that underlines renormalization group. But what I want to say is that if you consider the Hilbert space or the state space of a system with an Avogadro number of spins, that Hilbert space is huge, right? The vast majority of, in that Hilbert space, if you have a state, you could perturb it, right? The vast majority of those perturbations, right, would not affect long wavelength physics. The idea of renormalization is precisely the fact that if you squint enough, if you look at long distance physics, there in that exponential large Hilbert space, the vast majority of that don't matter. Means that they are irrelevant. The relevant physics is always a handful of coupling and terms. Remember how effective field theory or Landau's principle, we're writing that we took the Lagrangian density and just wrote down everything consistent with the symmetry. As you go to higher and higher terms in derivative expansion and higher field orders, what happens is that they're becoming more and more irrelevant. So very quickly, you're going to write down all the relevant terms you have, or marginal terms, right? And then you're going to stop. It's magical that such a simple theory will keep track of everything, right? Now, it's possible that your theory is non-renormalizable. In that case, it's a little bit more involved because the effect of the irrelevant terms, you can do perturbation theory up to a certain order, but non-perturbatively you have some problem. Anyway, so that was a tangent. Okay, yeah.
Were you talking about the toric code when you said the error correcting code that relates to RV?
Toric code is an exact quantum error correction code, but the one that I'm talking about is so. Let me just say a few words. It's a long story, but in the analogy between renormalization group and renormalization group of a local quantum system, a quantum system with a unique vacuum, the analogy goes this way: that errors or noise are UV perturbation flipping one of these. The encoded data is long wavelength, right? If this wavelength is, if this excitation is like this or down, this is my 0 and this is my 1, right? This 0 and 1 is protected against these tiny flips. That's noise and this is protected. Now, the story of this is approximately protected. So this is an approximate quantum error correction code. If you want to talk about exact error correction, then you have to have degenerate ground states. Toric code is a simplest example of that. Okay. All right, good. I got distracted, sorry. So we're reviewing the last lecture. Wilsonian RG, what did we do? We took the path integral, the generating functional of the theory, z lambda j, as we said, there's always a cutoff in quantum field theory. And this is all, I'm doing everything in Euclidean. This is due to Wilson, right? So think of momentum modes. This is the norm of the Euclidean momenta, right? So the Euclidean momenta in whatever dimension you are, if you're in 4 dimensions, 2 plus 1 dimensions, four Euclidean dimensions, this is the norm of that 4 vector. You have to path integrate this way, but you're going to cut this off, meaning that the path integral over phi is over all functions in Euclidean space that whose Fourier transform have momenta that with norm less than lambda, right? So such functions don't have UV details. This is all Euclidean. So what did we do? So another way of saying is that you do a path integral, but then you say the operator is, sorry. That's what the starting path integral is. What you do is you perform, so this path integral is a collection of integrals. What you're going to do to perform RG in the first step of RG is you perform the integrals in a thin momentum shell. That's what you do, right? You lower the cutoff from lambda to b lambda by explicitly calculating the integrals in this range. Good. So the way you do that is, well, if you want to perform the integral over certain modes, let's just give them a different name. So the mode that is phi k in this range that you want to integrate, and we're going to call it phi hat, so that is visible, right? And then this phi hat is only in this range. So write phi as phi plus phi hat. These are the IR modes, and these are the thing you want to integrate. In condensed matter, sometimes people call them the slow and fast modes. There is a version of this even in 0 plus 1 dimensions, like quantum mechanics. Yeah.
If I were to perform that integral in the free field theory, for instance, that restriction doesn't appear anywhere, does it?
Which restriction?
That momentum. So suppose I take the free field theory.
Free field theory, this path integral is just a bunch of independent integrals, right? Because the Lagrangian density of free field theory just factors. Right? So you have a bunch of integrals. So you do the integral. What does it in free field theory? What happens? When you perform an integral in this range, what happens? You don't generate new interactions. You just get a number, right?
Well, it has sources, those that integral with the sources isn't going to contain the cutoff, right? Because you have the free theory is e to
the source, no, it won't. Like, why is that? So here, d of phi of k. This is the action right? This is the schematically, and then your source term, this is still an exponent, is jk pi minus k, right? This is a Gaussian integral. So pick the mode in that range and perform the integral. What do you get? An overall constant, right? That overall constant doesn't matter in generating function, right? We saw that in quantum mechanics when we're doing path integrals in quantum mechanics. All right. So what we're doing is that we're writing the measure, the path integral measure as path integral measure with the cutoff, as the path integral measure with the cutoff b lambda, b is this number smaller than 1. And the explicit integral in this is infinitesimal thin momentum shell. All right, so here's what it is. So I'm going to write phi as del mu of phi, del mu. I'm going to plug this expansion in here. Good. You can see the analogy between this and spontaneous symmetry breaking. That's what we're doing. That's why I did that discussion earlier. So what happens? Well, let's just take this action and separate all the terms that only depend on phi, the low energy mode. So that will look like this. Then the other terms you'll have to integrate over is the integral. You have to perform the integral over phi hat. There is a phi hat. There's a part of the action that comes only from the phi hat, right? So there is half phi hat squared, half phi, the mass term, the cubic term, cubic quadric. Quartic term. And then there are the interaction terms, right? The mixing terms. Performing this integral what it will do is that it will give you a functional of phi, right? You take the log of that functional, put it up there, and that becomes your new effective action. It shouldn't be clear a priori that this effective action, the log of this thing, is just a bunch of local terms in the Lagrangian density. In the limit of b being very, very close to 1, you could convince yourself of that. So the effect of the high energy modes is to change the action of the low energy. Good? This is the principle of RG in action. Any questions? Okay. If the things that I want to highlight, and we did highlight this last time, is that under the Wilsonian RG, all terms allowed by symmetries will be generated. As you perform this thing, and you take the logarithm, you generate all sorts of terms. So this was one infinitesimal step. As you go to higher and higher orders, repeat this many, many times, and just bring it lower and lower. What you end up with is an effective Lagrangian density, which is the only way to know what that is just go back to Landau. We said, write down the most general thing possible, right? That's consistent with all your symmetries. That's it, right? You just have to write it down. So everything will be generated unless forbidden by symmetry. So now you should go back and doubt your whole starting point of quantum field theory. Why on earth did we write down lambda phi 4? What did it mean to say I had lambda phi 4 with that cutoff? That theory is highly fine-tuned. Because if I got my lambda cutoff teeny tiny bit wrong, I'll have all sorts of terms. That is extremely fine-tuned. In the coupling space, think of the space of all theories as the space of all Lagrangian densities, right? That's extremely fine-tuned. So what we're going to do next is that we're going to see how Lagrangian density flows, this functional flows in the space of couplings. That's going to be a renormalization group flow. Okay? And the idea is that it would be confined to flow in this infinite dimensional space of couplings, space theory space. It will be confined to a smaller space if there is a symmetry that forbids it. So in theories with large amount of symmetry, the flow is confined to some lower dimensional manifold. that's going to be a principle for us for defining theories that exist, right? Because we have control over the RG flow of it. All right, we're gonna get there. But what we saw was that basically what happens is that, well, as you perform these path interval, these I don't know why these are. Sorry. Everything looks good here. Okay. As we perform this, there is a piece there. So the couplings and the normalization of the fields will change. So what I've done here is that I've separated the quantum piece from the classical piece. Is it clear what is meant by that? No? Okay. No, it's not clear.
Are you just saying that the UV part is this quantum part? Is there small variations?
Let me give an example. So here, as I've written down the L effective, there is a phi 6 term. There can't be a phi 6 term generated out of phi 4 term without a loop, right? If you have a theory that has only phi 4 interactions, right? The only way to generate the phi 6 term is to have loops of this double thingies, right? So for example, let me try to draw one of those things. So you will have to have, let's see. So, well, we had all sorts of interaction terms. We had phi cube, all of that. But the point is that you cannot keep this tree level. Right? You'll have to have loops. So that's the first step of RG. The first step of RG is, it's a little bit of a confusing discussion. Sometimes people talk about RG only in one step. You just change the cutoff. The thing that we often do, which is more reasonable, is to say that there's a second step when we perform a scaling, rescaling, right? And what the net effect of this is that the cutoff comes back to the initial lambda. Because what you want to say is that at the end of the day, you want to say your theory is independent of lambda. But then in turn, what happens is that the scaling tells you what scale you're at, right? So the scaling we do, we often do this. Oh, let me correct this. We do this using a so-called wild transform. What you do is you define x prime as xb, by Fourier transform k prime would be k over b, right? These are your new, you change your meters and scales, right? And once I do this, and I'm going to get rid of b at the end, how do I know where the b is? How do I keep track of my b at the end of the day? So this theory, the thing that keeps track of scale is the metric. Metric tells you about your rulers. Under this transformation, how does metric change? So metric g mu of x prime is del x prime mu, well, actually, sorry, del x beta, del x prime mu, g alpha beta, right? Under this transformation, your metric goes from flat space to b minus 2 Euclidean flat space, right? So that's why you put this in here, in the second step. So you bring the cutoff back to initial value, but then the scaling is what you keep track of. And then we said one important principle for us was that we wanted, after you do these two steps of RG, for the kinetic term of the field to remain canonical, right? So that already tells you, so this is how the field transforms. right? So you that tells you how to define phi prime. Actually, it tells you how to renormalize your wave function. Also. Good. Yeah, is that clear? This is what we did last time. The reason, maybe I should not over-explain, but this confused me as a graduate student actually much longer than it should have. The reason that sometimes in the literature people do not do scaling as a second step of RG is that scaling is unnatural on a lattice. On a lattice, it doesn't make much sense to do scaling. Scaling is a genuinely continuous transformations. So there are some lecture notes you would read on condensed matter that are about RG. Most of the time, they don't do scaling. Sometimes people who want to be super careful, what they do is they keep track of the lattice spacing as a dimension-full parameter in the game, and then scaling is just saying, oh, your lattice spacing was epsilon, now it's 2 epsilon. Right? That's how you define it. But this is kind of artificial because there's no continuous symmetry. However, in the continuous field theory, there is a nice symmetry. That's why there's a distinction between the. You could take another point of view. For this reason, sometimes people just say, we're going to do RG with one step. Some people do that. I'm not a huge fan of that picture, but they're equivalent. These are not really, there's, yeah. Good. All right. We said that we do this. Let's do this for an infinitesimal momentum shell, right? So this is a thin momentum shell. This transformation becomes continuous, and what we're going to get is an RG flow, right? So you have the correlation function of the field with a bunch of momenta for the theory with the initial Lagrangian with the cutoff lambda. I can just suppress this cutoff lambda. If I'm doing RG in 2 steps, I just write the metric is flat. Then at low energy, the cutoff is unchanged because the 2 steps of RG will leave the cutoff unchanged. L effective has changed. Now you have some new metric, your low energy fields and their momenta as well. Good. Now you see the origin of the naive dimension counting at the very, very beginning of this course. If you ignore the quantum corrections and just pretend that everything comes from classical physics, then this is how the coupling runs under RG. A coupling G will change by the dimension of the operator, right? That's why when the dimension of the operator is positive, it's irrelevant. It decays in the RG. Well, sorry, when it's the dimension of the coupling, When the coupling is dimensionless, it's marginal. It's a marginal deformation. Lambda phi 4 in 4 dimensions, right? In 4 dimensions, yeah. What is the dimensionality of scalar field phi in 4 dimensions?
4 minus 0 2.
4 minus 2 over 2, which is 1, right? Phi 4 has dimension 4. You have an integral over 4-dimensional space. So lambda is dimensionless. So that is classically marginal. We tied that to renormalizability. So it's a renormalizable theory. When the dimensionality is negative, it grows in the IR. Example, what is the one deformation that pretty much every theory has that is relevant? Should know this for sure. Well, just think of the expansion of the Lagrangian density. What is the simplest term you could write down? There's a kinetic term, but what else?
Phi squared.
Mass term. Phi squared term, mass term. Mass is always relevant. Right? Why is that? Well, think of a scalar field. You could also think of the fermion, the count would be different, right? So m squared, well, mass is always relevant. What's the dimensionality of mass? Yeah. So it grows in the IR. This is the dimensionality of the operator that I'm writing next to it. So every theory, you should expect it to be massive in the infrared. The mass grows in the infrared, unless there's a symmetry that protects it. There's a symmetry that forbids the phi squared term, it will happen. And then irrelevant, as everything with like very high dimension operators, they will be irrelevant. Positive dimension, actually. So comments. Wilsonian renormalization group flows, so this is a summary, flows from the UV to the infrared. The UV cutoff is lambda in momentum space, Euclidean momentum. In dim reg, we treat 1/epsilon as the cutoff. Right? Remember in dim reg, so don't get confused. That's the analogous to lambda. Yeah, then what happens after 2 steps of RG is that our field and our couplings become scale dependent, right? So the cutoff comes back to what it was, but there's a renormalization scale. This is the scale of physics now, and this B lambda. In the renormalized theory, these correlators are independent of lambda, the correlators of the renormalized theory, but they depend on B. B is renormalization scale divided by the cutoff. So practically what's going on is that you write down a theory deep in the UV. When you renormalize it, what we did in renormalized perturbation theory is that we picked this UV scale to be extremely high, something absurdly high, right? Then the low energy physics is where you're doing your experiments, right? Of course, under this running, your field will pick up enormous amount of renormalization. Your couplings will pick up enormous amount of renormalization. This is the origin of the infinities in quantum field theory, right? If the cutoff was infinite, this would be infinite because the running would be infinite. But you pick a finite cutoff, there would be a large renormalization and there would be large change to the couplings. But that is what it means, right? You introduce this wacky, crazy scale as your cutoff. And it's only sensible if your renormalization scale, the physics of interest, is really much, much lower. Good. Let me say this again. If your renormalization scale is close, if renormalization scale is close to your cutoff, you should not expect a renormalizable theory. Right? Is that clear? It's only when you separate them a lot that irrelevant terms have time to die away. If you're just very close, there's no room for it. So what does this mean? Flip it around. When somebody comes and says to you that people prove that standard model of particle physics is renormalizable, it means that maybe it's a coincidence, but you would take this as an indication that very likely there's no new physics at higher scales for a while, right? How would you search for new physics? High dimension operators. You would search for irrelevant physics. If you find indications of irrelevant physics, that would be indications of, oh, we're near the cutoff. That means that there are degrees of freedom we missed. That's why we do a lot of precision measurements in standard model. We'll get there. Okay. Another thing that's important, we're not, yeah.
This might be unrelated. Is this the same idea as UV completeness?
No. So depends what you mean by UV completeness. That just means it's renormalizable. Yes, in that terminology, yes, correct. But yeah, actually, for the purpose of this conversation, when people say, that's the people say there is UV complete, they're probably phenomenologists, and what they mean is that it's renormalizable and it's all good. You don't need to. It's not a must to add degrees of freedom. It can exist without new degrees of freedom, except that we do know the neutrino mass is consistent with the blah blah blah. But that's a different story, right? When we talk about going forward in this course, we're going to talk about theories that exist. That's precisely what it means. Theories that are renormalizable, well, non-perturbative renormalizable.
So if you are calculating an scattering amplitude.
Yeah.
let's say, And you have your regularization, you have the 1 over epsilon there.
The
Right.
1 over epsilon doesn't quite survive, but yeah.
Yeah. In any case, you have the energy scale.
Yeah, you have the energy scale. That's not the 1 over epsilon. That's a
Okay.
cutoff.
You have the current.
You have the renormalization scale in the game.
Yeah.
Which is something different.
And so you have that scale, and when you go to an experimentalist and say, okay, this is what I got from the cross section. Well, when they look at that energy scale, what is an experimentalist going to say?
Oh, that's very good. Actually, they will see that the coupling, experimentalists plot the value of coupling they observe based on the scale. They have an experimentalist here. They can report on this. But for example, let me turn this around and tell you a little bit more about things that actually happen, has happened. People, especially in condensed matter, this is less common in particle physics because people talk about, they look at a system and they see some physics and try to write down some interactions that describes that physics. And for a while, sometimes they land on these theories that are non-renormalizable. There are interactions. There's a famous higher point fermion theory that was very, very useful for a very long time, right? So you land on these theories. It's perfectly fine. But as you go to higher energy, it's clear that the coefficient of that coupling will just go away, right? Because it's not normalizable, it's irrelevant. So as you go to higher energies, that has to decay. Similarly for mass. Also, remember charge of electron, E squared over, E squared over 4 pi, 1 over 137. That's a low energy. When you quote that number, that is in low momentum, right? At what momentum? You have to answer that question. There's a long story behind unification that is about couplings and how do you run, but we don't have to talk about that. Good. But here are some important things that I want you to remember. Integration is an irreversible process. If you take a function and integrate over it, you lost the knowledge of the integrand, right? There's no way of me giving you a number and you know that this is integral of a function. So in this sense, RG erases information. Squinting or averaging erases information. You average over something, so you lost it, right? So it's irreversible. There's a long story about this. So there are many manifestations of irreversibility of RG. That's a very important story in quantum field theory, blah, 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 but we don't have to talk about that. But I want you guys to know that. Another thing is that deep in the IR, it's only sensible to include renormalizable terms in the Lagrangian. Deep in the IR. Deep in the IR means what? Means compared to the other mass scales, right? If you're building an EFT that where actually you would deduce the cutoff based on how good your how good your theory is working, right? Like for example, we know that our the indications that we have from standard model, that standard model will break down the mass of neutrinos, points to many like 10 to, I don't know, 12, 14, gut scale physics, 10 to 12 GV, or even TV, yeah, GV, no, 10 to 16 GV. It points, it will be good all the way up there, because the indications that we have, there are things about standard model are missing, but that's a different story. All right, and then the last one I want to say is that fixed points of RG are scale invariant theories. The trivial scale invariant theory that you should know is del mu phi squared. Right? That's a scale invariant theory. Classically and quantum mechanical. This is a conformal field theory. But there are non-trivial conformal field theories. They're interacting conformal field theories. And it's one of the most important. If you are a field theorist, particle physics, condensed matter, what? If you just want to build a theory, you know about the theory space. You would like to classify all conformal field theory. So that's a whole different story. It's a semi-successful program in 2 dimensions, but in higher dimensions, it's very difficult. There's a lot of mysteries around this. There are Oh, I haven't, well, I think I'll include this discussion of universality. I don't want to go on tangents for now, but at the end, if you have extra time, remind me of talk about universality. Maybe I should say a few words. The very fact that the most UV physics is irrelevant tells you about universality. It means that this lattice system that you have, let's say you have an Avogadro number of atoms, like copper atoms, with some crazy interaction, microscopic interaction. Then you have another system which is like, who knows, like some particle physics field theory with some crazy Hamiltonian. And then a whole bunch of other things. You might have water molecules, right? But as you zoom out, as you squint a lot in all these examples, the way they're going to be described is universally using Landau's principle. Write down the most, identify the symmetries that will tell you about the particles, field content, right? These are the EREPs of your symmetry group. Write down the renormalizable, most simple thing consistent with your symmetries. This is the idea of universality. That's how the same field theory that describes Higgs can describe some phase transition in condensed matter physics. Microscopically, these are apples and oranges. They're very, very different. But from the low energy point of view, they're the same, right? This is the beauty of quantum field theory. Quantum mechanics is not like that. Quantum mechanics, the Hamiltonian will decide how things work. The beauty of quantum field theory is that you expect from locality in space that you just write down the principle of Landau. Symmetries appear in quantum mechanics as well. What is extra in quantum field theory is locality. You just write the most generic, consistent theory that's local. If I just like relax the notion of locality, hell breaks loose, right? It's just, you could write whatever. Good? All right, that's enough. Now, near a fixed point, say a trivial fixed point, we're going to take a trivial free scale invariant theory and add to it a bunch of couplings, right? We're going to add relevant operators, because if you add irrelevant operators and flow deep in the infrared, you won't see them. So just don't worry about adding them. That's a lie. But for now. Okay. How do you analyze what's relevant and irrelevant? Dimension counting. Your starting point would be just naive dimension counting. Phi squared is relevant, good. Del phi squared is relevant. Phi n depends on the power of n. Del phi n. They increasingly, as you go to higher and higher derivatives and higher powers of phi, they become increasingly irrelevant. There's one exception to that story. 1 + 1 dimension scalar field. What is the dimensionality of scalar field in 1 + 1D?
2.
What is the dimensionality of scalar field in space-time dimension D? You know this. Sorry? 0. Yeah. 2 - 2 / 2 is 0, which means that phi, arbitrary function of phi, is naively dimension counting renormalizable. Not derivatives. If you include derivatives, it goes higher. But arbitrary function of phi is renormalizable. The story is a little bit more complicated, or nicer actually, in 2 dimensions. More complicated because more complicated potentials can survive. Now, something for you guys to think about. If the dimensionality of space-time is larger than 6 space-time, besides phi, what's the dimensionality of phi? So 6 - 2 divided by 2, right? That is 2, right? Now, what is the dimensionality of phi squared? That's 4. What's the dimensionality of phi cubed? It's already 6. So this would have been irrelevant, would be a marginal term. But there's a problem with this term in the Hamiltonian. If you include in the Hamiltonian, what's the problem? Sorry?
Z2.
No, Z2 is symmetry. Oh, the Z2 symmetry. Yes, that's good. Z2, but there's another manifestation of this. The Hamiltonian, this Hamiltonian doesn't have a minimum energy, right? Because of the lack of Z2 symmetry. Actually, not because of that. So you would include 5, 4 is already irrelevant. The question comes up, actually, in higher than 6 dimensions, 7 space-time dimensions, this is irrelevant as well. So what would you write besides the free field theory? The question is for you guys to think about. Is there an interacting quantum field theory in higher than 6 + 1 dimensions? The belief is the answer is no. Good. All right. Now, what we're gonna do is real behind. Is we're gonna talk about our renormalization group flow of scalar field theory in space-time dimensions larger than 4. Okay. Then we're gonna talk about renormalization group of scalar field theory in dimensions near 4. I'm gonna pull some magic, tell you about some crazy stuff that work, define for you a theory that exists, hopefully if you have time, and then I'll comment on QED. All right. Consider the space of all coupling. So this is an infinite dimensional space. There's a mass term. I can't draw something infinite dimensional. This is lambda 4 term. This is lambda 6 term. This is lambda n. This is an infinite dimensional space. So what happens is I want you guys to imagine that relevant deformation, these directions are flows. When we say m squared is relevant, it means that this is how RG will push you. If you fine tune all the couplings to 0 and only include m squared, this will grow. If you only include lambda 5, 4, that's like fine tuning on this line. This is what we did before, right? You find some flow. Do you guys remember what the flow is? Well, no, you don't remember. I'm going to explain today. Yeah, I think I can't expect you guys to see that from QFT1.
Is the same flow as in differential geometry? The same?
No, the running of the coupling quantum mechanically. We did the calculation, but I didn't interpret it for you guys back then. But what I want you guys to know is that generically, this space is enormous, and these flows will have attractors, will do all sorts of crazy things. If you find anywhere in this space something that looks like this, I'm only drawing it 2-dimensional. This is a CFT, conformal field theory. That's an attractor, right? Those are important because this is a sign of universality. Many, many different theories flow to the same thing. You could also have these kind of things, right? It's a conformal field theory where it's unstable. We'll see examples of both of these. And then you could have things where there is like directions of stability and all sorts of directions of instability. The generic idea is that irrelevants are supposed to be stable, right? Things are converging. The idea is that, roughly speaking, there is a low dimension submanifold of relevant deformations where things are stuck on it. Everything else, even if you start off of it, will just you're attracted towards it. All right, that's enough talk. So most of what we're going to talk about for the next couple of lectures is about imagining this space and seeing some structure in this enormous theory space. So, I forgot to mention that in this theory, the UV theory could be arbitrary in higher than 4 dimensions. The UV theory for scalar field theory could be arbitrarily complicated, but if you have the Z2 symmetry, the low energy physics is expected to be massive free fields. So interacting scalar field theory in higher than 4 dimensions doesn't exist. It's not. We don't expect it to exist. I'm actually going to prove this doesn't exist, but it doesn't exist. Meaning what? Meaning that if you go deep in the infrared, the interaction is just going to die away, and you're deep in the infrared, it doesn't exist, right? It's fine-tuned. Let's talk about 4 dimensions. Is this part clear, by the way? We're getting to a point where I'm gonna actually give you tell you about theories that exist, theories that don't exist, and you're gonna end up with a handful of theories that exist. Okay, by the end of this course, you're gonna have a handful of it, and it's kind of magical that standard model does. But perhaps that's the punchline of the course. Lambda phi 4 interacting scalar field theory in higher than 4 space-time dimension doesn't exist. Ruled out. Everybody is with me? It's a naive analysis, but it holds up to the quantum standards. You could try to challenge it, but it will survive. The simplest way to see it survives is to do it for the simpler case. For the better case, the lower space-time dimension, the better behaved the theory is. To try to do this carefully in 2+1 space-time dimensions and see that scalar field theory in 2+1 dimension is non-interacting as well. Interacting theory doesn't exist, at least based on a one-loop discussion. Right? We're gonna see this. So even the whole the theory that I brainwash you guys with in part 1 of QFT doesn't exist. In 2+1 dimensions, m squared phi squared is relevant. This is marginal, classically marginal, based on naive dimension counting. So what's going to happen is that we're going to calculate. This is marginal. We're going to calculate the flow of this. We're going to see the quantum effects will make this coupling irrelevant. So at one loop, we're going to calculate the running of this and becomes irrelevant. Quantum mechanically relevant. Okay? So we're going to assume phi going to minus phi symmetry to forbid the phi cube term. This is the structure of the general structure. The m squared will have pick up some quantum running. There will be a term that has to do with the renormalization of the fields, right? These guys have to do with the renormalization of the fields. Hopefully you recall that. Right? Similarly for the coupling, notice that the naive dimension, this is 0. This is 1, sorry. This is 1. Because you're in 4 space-time dimensions. This is what I mean by saying that m squared is classically relevant. There's a b minus 2 sitting here. Whereas lambda is classically marginal. This is 1 here. So everything comes from the quantum mechanical flow. Whether or not the theory exists is about whether the lambda phi 4 term grows or decays in the infrared. We need to compute this running. Okay? We're going to compute it and we're going to find it. The computation comes from this diagram. This is really all you really need. Right? The one loop correction to phi 4 as you integrate this momentum shield, see where it comes from. One simple diagram. We did this last time, or I think we did this last time, but it's a pretty clear integral, right? We've done this a million times. Lambda prime becomes lambda minus 3 lambda squared over 6 pi squared log of 1 over b. So look at this. B is less than 1. This term is positive. Lambda squared over 16 pi 2 is positive. This is a negative sign. So at lower scale, lambda becomes smaller. That means this is the right direction. It flows towards 0.
How do you, given an arbitrary theory, how do you know what diagram gives you those?
Well, tell me about the theory, lambda phi 4. You have to look at the renormalization of the term, right? First of all, you really only need to focus on one term. That is one that was the classical marginal. If it was classically irrelevant, good luck. Quantum effects are not going to make it. There are some crazy exceptions, but those crazy exceptions are actually secretly not really marginal. But anyway, you start with a marginal term. There aren't many such terms. Lambda phi 4, there's only one thing, such a thing. You have to look at the one loop correction to this diagram, right? And how do you do that? By just doing the thin momentum shell integral, right? The diagram that contributes to this is this guy. This is that mode in between, right? This is what you have to integrate over. Everything else you draw is higher order than this.
What do you mean again by that circle in the symbol?
So you have the field phi. We split it into phi hat and phi. So this is phi for lambda up to lambda. This is phi up to b lambda. This is the low energy part, and then this is a part that is only between those two modes. The propagator for this, I'm drawing it with two lines. The propagator for the low energy modes, I'm drawing this way. This is what we integrate over, and this is the result of the integral. That's why it's finite, by the way. Right? It's a finite answer. This doesn't have any divergence issues. This integral, you just do it. Why is it log? Because it's a relevant deformation. It's a marginal deformation. You have the same number of same powers of k in the integrand as what your inverse powers of it that you're integrating. That's why logs are going to appear everywhere in all physical theories of interest. Because you're only going to do this for renormalizable theories, right? That's why RG is all about logs, at least perturbative RG. Perturbative RG is all about logs, right? Good. This integral you can do, right? It's pretty obvious. Do you see where it comes from, by the way?
It's just a standard moment.
Sorry?
It's just standard moment integral for the loop. Just standard loop.
Yeah, it's not even really an integral. Yeah, it's an integral with two lower and upper bounds that are very trivial. Yeah. It's from lambda to b lambda. Yeah. And here are your terms in the interaction. Where are they? Here are interaction terms, right? So here I've used this phi squared, phi hat squared. But there are you have other diagrams. Right? You have phi cube, for example. You see these guys are going to give you worse stuff. There is a phi 6 term. Let's just have some fun with this. There's a phi 6 term that's produced from this diagram. Right? Because I have phi hat, phi cube. This is phi hat propagating and phi cube. This is a phi 6 term. It appears. What else can I cook up? I can cook up all sorts of things, right? So I can have oh God. I can have this stupid thing, right? This is a correction. It's a two loop. But it's a correction to the propagator of the low energy modes. It contributes to them running a mass, for example, for the low energy mode. All right. All right. So when I said that all along, I said that I want to take B to be near 1. So what we're going to do is that near 1, we're going to take B del B. Why do we do B del B? We're going to see? We're going to introduce something called Callan-Simanzek. In Callan-Simanzek, we're always doing something like M del M, B del B. Do you know why? Because you expect B to appear inside logs, or B to some power, some parallel behavior. That's why in Callan-Simanzek, you write it that way. So B del B of lambda of B, which is this coupling, is 3 lambda squared over 16 pi squared. So if you just stare at this equation, the positivity of this tells you that it's doomed. This has a name, by the way. It's called beta function. The running of couplings as a function of scale. When the beta function comes out as negative, as positive, that is doomed. That coupling is going to go away in the infrared. It's irrelevant. When it comes out as negative, it's going to grow in the infrared, and you're UV safe. UV nice. The discovery that QCD or Yang-Mills theory has negative coupling beta functions was the only reason that people did not discard quantum field theory in the 70s, 60s. Up until the 60s and 70s, the main line with QED doesn't exist. We're gonna see that. So QED is bad. So people thought, oh, QED is bad. Nobody has seen lambda phi 4 theory in lower dimensions because it exists in 3 dimensions. So people thought like we're going to discard quantum field theory. It's not going to go anywhere. There's a very famous calculation of beta function for QCD. And when people discovered this negative, then Nobel Prizes were given. There's a long story afterwards. I'll tell you the story of there was a sign mistake in the calculation, blah, blah, blah. All right, so this is called the beta function. We don't write it often in terms of B. We write it in terms of the physical scale, right? What is B? It's the physical scale divided by the cutoff. So we write it like as M del M. This is usually what's called the beta function, right? It describes the flow of lambda. Good. Now, when you see the flow is order lambda squared, what does it tell you? It tells you that this, whatever this correction comes from, it will have two of the original vertex, which means that it definitely has a loop in there. So this is a quantum correction, right? Lambda squared terms were always loop corrections. So as you, this is, we're going to expand this in lambda. Remember, we're doing perturbation theory in small lambda. So we're going to look at the lowest order in lambda. Higher order in lambda are higher order in loop expansion. Good. In the infrared, there's no interacting scalar field theories in 4 and higher dimensions. Is anyone curious about Higgs?
Higgs is the 5-4 kind of theory.
This is a lambda 5-4 kind of theory. So why does it exist?
If you have a beta function which will cross 30, what would
Ha.
that?
Okay, very good. Anyone wants to say something? You mean for lambda equals 0, it's non-zero. You're saying that beta of lambda equals 0 is non-zero. Anyone want to say something? We're going to see an example of that in a bit. What is a strongly coupled fixed point? What are the beta functions at a fixed point? Free or not? What are the beta functions? 0. So if you have a theory with interactions that has, oh, sorry, this is the opposite. When beta of non-zero lambda is 0. But lambda, yeah, beta of lambda equals 0 could also be non-zero, yeah. There's a, just to tell you something, lambda is not an observable in a theory. That lambda is scheme dependent. So another thing that we're going to learn as we go forward is I'll tell you that what are actual physical observables and what are made up. We're going to see that lambda is not like so shifting lambda, the zero value of lambda is not necessarily a very physical observable. At one loop near a fixed point is okay, it's well defined, but that phenomenon you just described, you're not going to ever see at one loop near a fixed point.
I think I have seen it before.
It has to be higher orders. Yeah. What theory are you thinking?
It's for the Higgs, if you look at the subcoupling.
But that's that's not a lambda 5-4. That's like a, well, we're gonna see Higgs sits inside a larger theory. There are all sorts of other excitations, so there are more couplings. Yeah. So in this higher dimensional space, right? There's this like crazy higher dimensional space. This is my schematic thing, right? There are all sorts of flows. If they cross any of these lines, for that value of coupling equals 0, you have a non-zero flow.
I thought it pointed to the fact that you have been inclusive of that. Like if the self-coupling crossed through the 0 point.
I'm not sure what self-coupling is, but let's talk about this a little bit more. Yeah, I'm not familiar with that context. All right, now here's a crazy magic. What are we gonna do? We're gonna study scalar field theory in less than 3+1 dimensions. All right, and we're gonna do something a little bit crazy. but we're gonna see the power of it. Imagine lambda phi 4 theory. Below 3+1 dimensions, this is how it flows. You could do the integrals. Now, this is the expression, and of course, you send d to 4. There's a gamma function here. There are these things that cancel out, and you get the answer. That's actually in part why we do we love dim reg, because the results of dim reg come dimension dependent. Come out dimension dependent. So indeed, this is the full expression. Do you see where this comes from the integral? Well, it's a one-liner, so you can see that. This refers to the fact that classically it is relevant, b to the power of d minus 4, right? Because it's a negative power and lower than 3+1. B is less than 1, so it grows. Good. What we're going to do is we're going to do 4 minus epsilon dimension, right? But not as a regulator. We're going to just take the idea that we have a theory that literally lives in 4 minus epsilon dimension. This is the beta function you're going to find for it. So beta function is going to be 3 lambda squared over 16 pi squared. When you, as I said, what you want to do is you want to, we're in perturbation theory. We want to linearize this. We'll expand in lowest order. In lower dimensions, epsilon, which is 4 minus d minus 4, sorry, 4 minus d comes out. 4 minus d comes out as a linear coefficient here. What does it mean? You start at lambda equals 0. There's a competition. There is a term that comes from loop integrals that are pushing you away. There is a term from the low dimensionality space that's fighting against it. In perturbation theory, you end up with a new fixed point at finite lambda star. That's where this is 0. So this is a new fixed point. What is crazy about this is that we found a new fixed point in perturbation theory. So there's a full RG from a UV theory deformed by some perturbation, lambda phi 4. You flow all the way, the whole thing is within perturbation theory and hit a new fixed point. But we pay cost for this. It's dimension very close to 4. What does that mean? We don't really know. But this is a fixed point. It's called Wilson-Fisher fixed point. Then the craziness starts. You could take epsilon to be 1. So you could talk about fixed points, Wilson-Fisher fixed point in 2+1 dimensions. And indeed, this magic works. Why is this important? Remember that we want to stay in perturbation theory, right? The moment we cannot, there's no chance of integrating this thing for large amounts, for a large flow. If you're outside the perturbation theory, higher and higher loops will give you higher order correction, and that will significantly modify your flow. So there's no hope of integrating this explicitly. I'm going slower than expected, but that's fine. So here's a diagram of what it looks like. You have a new critical point. This critical point is the 0 of 3 lambda squared over 16 pi squared,
yeah,
is equal to epsilon critical, right? That means that lambda critical is F16 16 pi squared 4 minus d over 3, right? This is our fixed point, Wilson-Fisher fixed point. So here's a theory that said lambda 4 equals 0. You deform it, it flows this way, and the flow stops here. This is a new fixed point. The m squared at this new fixed point, this is Wilson-Fisher fixed point. At this fixed point, m squared is still a relevant deformation, so this will move away. However, all the other directions will flow this way. This is an attractive fixed point. That's important. We'll see examples of fixed points that are not attractive way later, not now. So we could trust this within perturbation theory because we're in this d4 minus epsilon dimension. In general, there can be strongly coupled fixed points in the infrared. So this kind of analysis is not going to get you anywhere. The best hope we have is just hope to just abstractly start building a new theory that studies or aims at classifying conformal field theories in general, so that we can know about what kind of theories we can land in infrared. Land on in infrared. And d equal 2, we said that all phi ends are marginal, so there's been a lot of progress in understanding conformal field theory. It has to do with the fact that conformal symmetry in 1+1 dimensions is enormous. The conformal group is enormous. Let me not comment on that. All right. Any questions? Okay, I ran out of time. I didn't even get to Callan Szymanczyk. Let me. Yeah, I think if I start, it's a can of worms. If I start talking about Callan Szymanczyk, how much time do we have? Is it 5:45? Yeah, I'd rather take questions and discuss this a little bit more, and keep Callan Szymanczyk for next time. Because I got only halfway through this lesson. All right. So that's what the story is. We start, so from the low energy observer point of view, I go to a lab and I'm trying to model some physics. All I know is that whatever physics I'm trying to model has an insane number of ingredients, fundamental particles, and these guys are interacting locally. These are basically all I know, right? There's some sort of notion of locality. This can happen in a tabletop experiment for some metal. This can happen, theory of electrons or something. It could happen in fundamental physics. Oh, actually, I want to make a comment about this. So in our modern way of thinking about quantum field theory, there's two ways to think about it. One way is say quantum field theory is always in the infrared of some crap in the UV, right? The thing in the UV is really, really complicated. You don't care. You're just going to build this as an effective field theory. In this way of thinking about stuff, everything in physics is effective field theory. Renormalizability just tells you that, well, it's effective for a while. It's working for a while, right? That's what it tells you. The other way of thinking about this that I've been saying indirectly many, many times. So this is what quantum field theory is in the first point of view. Quantum field theory is an infrared phenomenon. Standard model is actually this way. We use standard model this way. We all the EFTs that we see in lab are also like this. The other point of view is to say, to focus a lot on conformal field theories. Conformal field theories that are well-defined. UV, IR doesn't matter. Quantum field theories are deformations of these things. So you start with a CFT, deep in the UV, you deform it, and then you flow. Quantum field theory is what you get from flowing down the RG of a relevant deformation of a CFT. This is the high energy perspective. What quantum field theory is. Quantum field theory could be defined as you take a CFT, you classify what the relevant operators are, you take the theory, deform it, you flow. Whatever you get deep in the infrared is a quantum field theory. Now, the space of quantum field theories could be this coupling space. You could think of it as there is some sort of a topography. It's like there are valleys and there are like peaks, right? At every saddle point sits a CFT, right? At every fixed point sits a CFT. Some of them are peaks, so you flow down. Some of them, so those deserve to be viewed as UV theories. Some of them are in the infrared, right? So it is kind of interesting Yeah, understanding this structure is very important. A lot of search has gone down in this direction of if you model a theory, right, in the UV, in the infrared, you build a CFD. Oh, sorry, you see it first. Say you have a CFD in the infrared. We see them a lot. Now the question is, if it comes from a UV CFD, because the UV, if there is no fundamental, if you don't take quantum gravity into effect, it has to come from a UV CFD. Is there any way for me to, based on my infrared theory, to know what UV CFDs could not come from? Can I rule out possible UV theories? This is going in the opposite direction. We said that RG is irreversible, so it erases information. But you're still trying to see, well, okay, if it erases information, maybe you could define functions in a CFD that are monotonic under a RG flow. These would be measures of the amount of degrees of freedom in there. Then, when you see a CFD in the infrared and you measure that value, you know that any other CFD with a lower value than that cannot be your UV theory. This is sort of C theorems, and it's been, again, a successful story in 2 dimensions. In higher dimensions, it's very difficult. All right, are there any questions? So I already made 2 types of comments about existence of theories. One of the comments I made was that in 6 dimensions and above, there are no relevant deformations. So if you start from a CFD, if it's free, you're not going to be defining a quantum field theory. You're defining a quantum field theory by flowing down. Or even if you have a crazy non-interacting CFD, it's an isolated point. It's not connected to anything else by flow. It's a crazy concept. They're isolated points. We have examples of such theories from fancy mathematical physics. This is one thing. The other thing we talked about is that just an infrared point of view, you're in 4 dimensions, and you identify that you have Lorentz symmetry, and you identify you have a degree of freedom that is transforms as a scalar and has Z2 symmetry. That theory is free, must be free. There is no chance, right? This is a very infrared point of view. All right, are there any questions? I didn't get to Kalam-Simanzik, but that's a long story. We're going to do that next time.
I have a question very important one. And there was this integral that diverged after all the regularization. It's an integral that goes like integral of x over 1 minus x from 0 to 1. That explodes. Is that normal to see that kind of behavior?
No, which integral that there should not be divergences. After you put the cutoff, the dim reg, everything should remain finite.
Yes, things that apart from the one.
I see. You're talking about yeah. I know what you're talking about. That has to do with infrared divergences. That's not the UV divergence. That's an infrared divergence. Are you talking about this diagram? Or are you talking about
this infinity?
This?
No, this infinity. Well, that one as well. What?
Yeah. Okay. Yeah. It has to do with infrared divergence.
Okay.
I think, if I remember correctly. Yeah. Well, if the dim reg didn't cut it off, must be IR. Mm-hmm. But one way to know whether it's IR or not, look at where you said x near 0 is where it diverges. Mm-hmm. Let's track that. Yeah, you made a bunch of change of variables. See in the original degrees of freedom what momentum corresponds to that is running in the loops in that small variables, because you made a bunch of change of variables, right? You find these L variables, all of that. I believe that's an infrared thing. All right. Any other questions?